Okay, year 12. This video is going through the documents called recent, so we'll need a new pen, gas, something like recent gas calculations, something like that. Recent ideal gas, maybe it's called. I need a new pen. Bear with. I'm recording this in school, in the little science staff room, so I've got to be a bit quieter than normal, so I hope the sound quality is okay. Right then, this question fills people with dread because it looks like some sort of random physics question and you end up thinking, hang on a minute, I didn't sign up for physics. But we just got to read it first and see what happens. The diagram represents two glass flasks, P and Q, okay, connected via a tap. So as per usual, I've not practiced these questions, so you're just going to see me maybe make mistakes or whatever. Flask Q with a volume of 1 times 10 to the 3 centimeters cubed. Alright, so I'm already thinking units. So I've got flask Q with a volume of 1. So the volume of this is 1 times 10 to the 3 centimeters cubed. So that's 1,000 centimeters cubed. Alright, so if you want to turn centimeters cubed into meters cubed, you have to times by 10 to the 6. So, divide by 10 to the 6. So 1 times 10 to the 3 divided by 1 times 10 to the 6 equals 1 times 10 to the minus 3 meters cubed. It's filled with ammonia, NH3. Now, something that you'll get from Dr. Halliday when this video eventually comes to you, it doesn't matter what gas it is, all right, in terms of its volume. So the ammonia might come in useful later if we're working out MRs. 102 kilopascals, that's units. Remember, this is all about units. Maybe I'll write that on the top again. Units. There you go, I'll do my little tattoo. Units. 102 kilopascals. 102,000 pascals and 300 Kelvin. I'm happy with the units there. 300. So I've got a V, a P, and a T there. If you've got a V, a P, and a T, and they give you R, you can work out moles in here. The tap is closed and there is a vacuum in flask P. So at the minute, this is shut, so you've got this volume. Calculate the mass of ammonia in flask Q. So firstly, remember, we approach these with, well, it's not a conspiracy, there's no missing information, so I must have enough information. You've got a P, a V, and a T. So I've got PVT, mass of ammonia. Well, mass is MR times moles. So if I can work out moles, and I've got the MR, we should be able to do this. So first thing I'll do, I might do MR of ammonia is 14, 15, 16, 17. MR equals 17. Probably not worth a mark, that. Moles. PV equals nRT. N equals PV divided by RT. If you're struggling with that conversion, that rearrangement, sorry, you shouldn't be doing A-level chemistry. Promise you, you really shouldn't. Right, N equals PV over RT. So then you would go 102,000 times V times 1 times 10 to the minus 3 divided by 8.31 times 300. Okay, I haven't got long to do this, so 102,000 times brackets 1 times 10 to the minus 3 close brackets equals divided by 8.31 times 300 0.409 0.0409, and that's moles. I encourage you to write these words after moles or grams. So I've got an MR over here and I've got a moles, so all I've got to do is times them together. So times that by 17 and you end up with 0.6955 grams. 0.6955 grams. Says appropriate number of significant figures. 1, 2, 3, 1, 2, 3. 3 sig figs. 0.695696 grams. There's my answer. Thank you. Right, going to turn over, check that. Okay. There we go. Allow 0.696, allow 0.695 or 697. So that'll be some sort of rounding thing. Cool. 1, 2, 3. All right, remember what my approach was? So I'm always panicking that I'm going to get these wrong. When I turn over, there's a very good chance I could have made a mistake, because there's loads of places you can make a mistake on that. But just stay calm and check the units. All right, this is the tricky bit, I suppose. When the tap is opened, the ammonia passes into flask P. So I'm going to open this flask and it's going to pass into here. So the idea behind this then is that those moles here are now shared between two. All right, we just worked out how many moles there were. By the way, I'll just write that up there because it's from the previous question, 0.0409. And that's now going to be shared between the two flasks. Okay, when the tap is opened, ammonia flashes into flask P. The temperature decreases by 5 degrees C. That's some sort of physics thing that I can't remember what it's called. Oh, someone will know. It's how fridges work. Anyway, not the point. The temperature decreases by 5 degrees C. The final pressure in both flasks is 75, so the pressure will equalise. Okay, so what have you given me? I don't know what I'm doing yet. So, temperature decreased by 5 degrees C. That's 295 Kelvin. All right, everybody. Sorry about that. I ran out of storage space on my phone. I carried on talking, and basically I lost a load of footage. So I'm going to go back to this point. So what we've got then, so we realised I confused my P's and my Q's before. In this bit then, we know that PVNRT. So pressure. The new pressure in both flasks is 75,000 pascals, because I'm not going to fall for the units. The new volume I'm trying to calculate. Now this will be the volume of P and Q combined. N equals 0.0409 moles from the previous question. That's the amount of ammonia that you had. R equals 8.31 and temperature equals 295 Kelvin, because it says the temperature is decreased by 5 degrees C, and previously up at the top it said it was 300 degrees C. So if you've got PV equals nRT and you rearrange to get V, you get nRT divided by P. If you do that and plug those numbers in, you will get a volume for the both of the flasks combined. So it's 0.0409 times 8.31. Oops, I've written 831 there. 8.31 equals times temperature 295. So there's my top row, and I'm going to divide that by the pressure, which is 75,000. So then, oops, I pressed equals again. Let me do that again. 0.0409 times 8.31 equals times 295 equals divided by 75000. Okay, equals 1.3368, etc. times 10 to the minus 3 meters cubed. And that is the combined volume of P and Q, so that's worth 2 marks. The final mark is for taking that value and minusing the value of flask Q. So then it's 1.3368 times 10 to the minus 3 minus the volume of flask Q, which was, I seem to remember, is 1 times 10 to the minus 3. And you end up with 0.3368 meters cubed. Oh, they're horrible here, you know. So you get up an answer in meters cubed, and then it says it needs to be in centimeters cubed. Right, if you've got a meter cubed, so you need to times that by 1,000,000 in the end. So whatever answer you get here, you'll then times that by 1,000,000. So you're going to end up with 0.3368 times 10 to the minus 3. You're going to times that by 3. I think it's 336. So you're going to times by 10 to the 6. There's some horrible unit conversions there. Is it 300-ish? Yeah, 342, but anywhere in this range due to rounding. Alright, what did I do? Well, I know there's some difficult unit conversions there, but I looked what they're giving me, P, V, N, R, T. I changed the units over, and then the only trick here was realising that the volume at the end would be the volume of both, and that the number of moles, if you only got 0.0409 moles in there, that will now be spread between the two, so N was constant. I know I messed up P and Q, but I don't really care because I still got the right answers. I realised my mistake, and it was alright. Okay. A student determined the relative molecular mass of an unknown volatile liquid in the experiment as shown in the diagram. I actually found some of this equipment in C2 the other day, all dusty. Must have been used years ago. So we can do these experiments actually. So you've got a volatile liquid. Now volatile means a liquid that turns easily from a liquid into a gas. Alright, so if you have a liquid and then you heat it up a little bit, it'll turn into a gas. The student used a hypodermic syringe to inject a sample of liquid Y into a gas syringe in an oven. So because it's in an oven, they squirt the liquid in here and it turns into a gas. And that gas will expand and it'll push this plunger out and it'll have a volume. So a little bit of liquid will expand to fill a volume of gas. At the temperature of the oven, liquid Y vaporized. Okay, so they're going to squirt a liquid in here, it's going to come in here, it's going to turn into a gas and push this syringe out, and that will be your volume. Alright, so what have we got? The mass of the hypodermic syringe and the liquid before injection, the mass of the hypodermic syringe and the liquid after injection. So I look at those two and I know by looking at this that they've injected 0.21 grams of Y has gone into here. Grams. We can turn grams into moles when the time is appropriate. Oven temperature 98.1. You're not catching me out, so you're going to plus 273 onto that. 98.1 plus 273 equals 371.1 Kelvin. There's my temperature. So there's T equals that. Pressure equals 102,000. They're not catching me out there. And V, I take this is the volume in the gas syringe after injection. So this is the volume of gas that you've got. 85 centimeters cubed, which is 85 times 10 to the minus 6 meters cubed. What's that tattoo say? It's all about the units. Okay, I'm just going to write this out better. 102,000 pascals. So there's my T, my P, and my V. And you always got R, which is 8.31. Define the term relative molecular mass. You can define that, please, yourselves without me going through it here. Use the experimental results in the table to determine the relative molecular mass. Relative molecular mass is MR. How do you work out MR? Mass, Mr. Moles. Alright, so MR is mass divided by moles. In other words, let's find the moles. We've got a P, a V, a T, and an R. P, V equals nRT. Let's work out the moles. N equals PV over RT. Let's collect the data from up here. 102,000 times volume 85 times 10 to the minus 6. 10 to the minus 6 divided by 8.31 times 371.1. This is giving me the number of moles. I'm feeling anxious now because my lesson's about to start. 102,000 times 85 times 10 to the minus 3. 8670. No, 10 to the minus 6. Mistake. 102,000 times 85 times 10 to the minus 6. Sorry. Then I'm going to divide that by 8.31 times 371.1. 2.81 moles equals 2.8114 times 10 to the minus 3 moles of this gas Y. That's how many moles have gone in there, and I've worked that out because it filled that much volume. So I know the moles, and I also know, the grams. So I've got that many grams, 0.21 grams, mass divided by mole. Okay, 0.21 grams divided by 2.8114 times 10 to the minus 3 moles will give me an MR. 0.21 divided by 2.8, I should do the answer here, shouldn't I? 2.8114 times 10 to the minus 3. 74.69, 74.6995. That's the MR. Relative molecular mass. How many sig figs? 3. 74.7. Alright, units for an MR, it's actually grams per mole. There's that many grams in a mole. So 74.7 grams per mole. Let's have a little look. Please, God, let it be right. Yay, check that out. 74.7. Okay, what did I do? I made sure I got my units right. I realised I had P, V, N, P, V, R and C, so I thought, well, I'll work out N. I also know that if they ask me to work out MR, the only way I know to work out MR is to do mass divided by moles. You only have a limited number of skills, so it's realising that the question is just asking you to do a limited number of things. How do they make this difficult? By giving you a strange situation that you might not have fully understood, but really, it all looks alright. It's all about the units. Next. Done. Some of the liquid injected did not evaporate because it dripped into the gas syringe nozzle outside the oven. Explain how this would affect the value of the MR. Right, so what they're going to say is, so you got that. Okay. So some of the liquid dripped out, but they're saying that it didn't turn into gas. It didn't contribute to this volume. Right. So you will weigh it after, and you will think that more mass has gone in. You will think that a big massive Y has gone in. So you will think that mass is a bigger number, but the volume and the number of moles from the calculation will be the same. But the volume will tell you, the number of moles from your calculation will be the same. So you're going to be dividing a bigger number by the same number of moles because you think there's a bigger mass gone in. Oh yeah, you think a bigger mass has gone in. The number of moles will be the same from the calculation. So you will come out with an MR that is too big. Is that right? Yeah. You'll come out with an MR that's too big. MR too big. And I'm looking there. It's done it in another way. It says you won't get the full volume because of the mass. I think that doesn't... There's a funny way of thinking about it. Your volume won't be as big as you expected because not all of the liquid went in. Lower volume, so the MR would be greater. I've said you think that the mass of liquid is bigger, so mass divided by moles, the MR will be too big. Either way you think about it, you will overestimate the MR. So check the time. I've got 5 minutes, and I've got a lot of questions to do. And I started coughing. That was only my first cough. Second cough, and I'm done. Right. So, I think I'm going to have to pause there, and I will edit this together when I'm at home. I'm going to do question 3 at home and question 4. Let's have a little look. So I've just got question 3 and 4 to do. Cool. Thank you. Okay, so I've decided to go through question 3. Question 3, an experiment was carried out to determine the relative molecular mass of a volatile hydrocarbon, same deal as above. So what I said on just previously there, re-recording this, mass 0.194 milligrams, you have to convert that to grams. Kelvin I'm happy with, pressure I want to turn into pascals, centimetres cubed to metres cubed, you just literally write 10 to the minus 6. PV equals nRT, so N equals PV over RT. If you plug these numbers in here, you will get a value for N in moles. Then if it wants you to work out the relative molecular mass, which is the MR, MR equals the mass, which is 0.194, divided by your value for N. That question's absolutely fine. Very similar to the previous one. It's all about unit conversions. Unit conversion there, milligrams we don't use in science. Kilopascals we don't use in a PV NRT. Centimetres cubed we don't use in PV and NRT. Turn it over the page. Relative molecular mass, whatever it was. 5 marker though, for all those unit conversions. The correct precision, it says here, correct number of significant figures is 2 significant figures, please. Because this is to 3, this is to 3, this is to 3, this is the 2. That is the least significant figures. So that's what you do it to. Next page, I'm about to start teaching, so I'm panicking here and making mistakes, I feel. Analysis of a different hydrocarbon shows it contains 83.7% by mass of carbon. Calculate the empirical formula. Hydrocarbons are made of hydrogen and carbon only. That's GCSE. Alright, so it contains carbon, hydrogen, 83.7. That means this must be 16.3. Divide by 12. Divide by 1. 83.7 divided by 12 equals, this gives you your raw ratio, 975, and that's 16.3. So you got 6.975 to 16.3. You divide both sides by 6.975. 16.3 divided by 6.975. You end up with this, 2.33. You end up with a 1 to 2.33 ratio. You should spot this as being 2 1/3, so you need to times both sides by 3. That is 3 to 7. Empirical formula, C3H7. Molecular formula. Right, the molecule weighs 86. So I'm going to work out what C3H7 weighs. 12, 24, 36, plus 7 is 43. 86 is twice 43, C6H14. Right. Question 4. Right, what have we got then? A toxic chloroalkane has a boiling point of 40. Okay. They determine the MR of it by injecting a sample into a gas syringe at an oven. Right, Okay. Temperature. You need to add 273 to that to get it into Kelvin. I'm not going through all of this. You can deal with it yourself because I'm about to teach. 100,000 pascals. Mass of the hypodermic syringe before, mass of the hypodermic syringe after. So I can see here that 0.27 grams has been injected. I think, just mental arithmetic. 0.27, it's there, 0.27 grams of this sample. This produced a volume in centimeters cubed of 105, so that's 105 times 10 to the minus 6 meters cubed. So I've got, what have I got so far? I've got a temperature, PVNRT. P, 100,000. V, 105 times 10 to the minus 6. N, don't know. R, 8.31. Temperature, 273 Kelvin. No, plus 93. 273 plus 93. 273 plus 93. 366. Alright, question 4 then. All you're going to do, N equals PV over RT. That'll give you the number of moles. I hope you agree. If your units are correct, you'll get that right. And then to work out the, does it work out the MR? So complete the table. Volume before, volume after, 105. That is just 105, isn't it? Yeah, okay. So I had to do that, 105 centimeters cubed. N equals PV over RT. You'll get your value of N. Just looking at the answers here just to make sure I'm not setting you up to fail. Once you've got your value of N, you are then going to divide the mass, 0.27 divided by N. Just check, where's that mark scheme gone? There's a tone, 0.27, there we go. 0.27 divided by your volume for the moles, and you get an MR of 79.1. Alright, so we've done these prior. The other questions are very similar to this. I'm getting a bit lost, and I've got to go and teach year 11, which I'm not excited about. So then you are told, I accidentally wrote an answer on here to a different question. 79.1. Well, one of these two weighs 79.1. You work out which one it is. Okay, it's up to you. Suggest a reason, other than apparatus inaccuracy, why the MR value determined from the experimental results differs from the actual MR. Explain your answer. Whoa. Okay, I'll have to think on about that. 2 marks. Suggest a reason other than experimental inaccuracy. But I've got to go. I haven't got time to think. Well, those answers on there. Okay, I'm having a little look now. Suggest with a reason an appropriate safety precaution that the student should take using the toxic chloroalkane. Well, it's toxic, so wash hands after use. Don't inhale the vapor. Maybe use a fume cupboard. That's a good one. Fume cupboard. Reason, toxic. Removes the fumes or something like that. It'll kill you if you breathe in those fumes. This one, why is the MR different from the MR? Right, how do you work out MR? Well, MR, you need to work out moles equals PV over RT. So, I think I've looked at the mark scheme. It says if your volume was wrong, if you measured the mass wrong. Oh, right, so apart from accurate apparatus inaccuracy, yeah, human error. If you measure the mass wrong, you're going to get, because MR equals mass divided by moles. So if your mass was measured incorrectly, you'll get a wrong MR. If your volume was measured incorrectly, you'll get a wrong number of moles. There's all sorts of connotations written on here. Oh, but I'm done. That's not my best video ever, but I've had to try and get it done in school. I hope that's okay for everybody. Thanks.